In 1609, Galileo Galilei looked at Jupiter with his telescope for the first time. He discovered the planet was not alone, but instead was attended by four stars that appeared to change their positions from one night to the next. He quickly realized that these were not stars at all, but rather moons of another planet. He published his observations in the Sidereus Nuncius, otherwise known as the Starry Messenger. A print of Galileo's revolutionary book now adorns ESA's Jupiter Icy Moons Explorer spacecraft, or simply JUICE. Set to launch aboard the Ariane 5 rocket on April 13th, JUICE will embark on an 8-year journey to reach the giant planet. There it will spend the next 5 years making a series of flybys of Jupiter's icy moons, Europa, Callisto, and Ganymede. These moons are Jupiter's water worlds, each covered in a thick layer of ice. Europa and Ganymede are definitely geologically active, which means their hot interiors are keeping the water liquid underneath their icy surface. In other words, Jupiter and Ganymede, and maybe, possibly Callisto, all have liquid water oceans underneath their exteriors. JUICE will make the most precise measurements of these moons and eventually will settle into an orbit around Ganymede, which is the largest moon in the solar system. And this will be the first time a spacecraft has ever entered into orbit around another planet's moon. As of this filming, JUICE is being prepared for launch at the Guiana Space Center in Kourou, French Guiana. 10 years of work and I don't know how many man-hours are about to culminate on its launch on April 13th. Then it begins its 8-year journey to reach Jupiter, bringing with it the most massive scientific payload ever sent to the giant planet. There are so many questions we have about Jupiter's icy moons. How did they form? What drives their magnetic fields? What can their story tell us about the formation of the solar system in general? And do all of them really have liquid water oceans? And if so, are they in fact habitable for life as we know it? To find out more about the mission, I sat down with Dr. Olivier Vitasse, the JUICE mission project scientist. We talked about JUICE's mission objectives, its science payload, the long, strange trip it's about to take, and how it will eventually join forces with NASA's Europa Clipper mission when it arrives at Jupiter in 2030. Now, to say that Dr. Vitasse and the JUICE mission team are super busy right now getting ready for launch is an understatement. So I was so thrilled that Dr. Vitasse would take some time out of his insanely busy schedule to chat. And so without any further ado, I bring you my conversation with Dr. Olivier Vitasse. Olivier, thank you so much for joining me today, and I'm so looking forward to learning more about the JUICE mission. How are you?
Yeah, good. Hello, Christian. How are you? I'm fine. Good afternoon, good morning. Happy to talk about JUICE.
I was wondering if you could maybe just start off with the boilerplate. What is JUICE about? Why are you trying to reach the icy moons of Jupiter?
So JUICE, it's a planetary mission from the European Space Agency. We launched in less than a month, the 13th of April from Kourou, and we prepared this mission for more than 10 years already, and we still have many years in front of us. So the goal is really to go to Jupiter, in the Jupiter system, to enter in orbit around Jupiter, and to make many flybys of the 3 Galilean satellites of Jupiter, which are Europa, Ganymede, and Callisto. And at the end of the mission, we enter in orbit around Ganymede. Ganymede, it's really our prime target, and the goal is to explore those icy moons to understand what they are, and in particular to understand better their liquid ocean underneath the surface, and to study the Jupiter system in general.
So you're not going to Io. You mentioned the icy moons. Was Io ever a consideration for this mission?
No, Io is not considered for this mission because the goal was really to explore the icy moons, and Io is not really in this category. So it's one thing because we want to explore whether around a planet like Jupiter we have places which are called habitable. So that means there is interesting ingredients for life in there, and that is linked to the liquid ocean. And Io is really in a different category. Io, it's a volcanic moon, so it's really different. So that's the first reason. And the second reason is that to design or to prepare a mission to Io, it's very, very complicated from the technical and engineering point of view, because Io is very close to Jupiter, and then it's really embedded into the very harsh radiation environment.
You mentioned the icy moons are a target because you want to determine if there is an ocean underneath their icy surfaces. How would you be able to do that remotely if you're not going to be able to land on the surface and drill down and see if you can go swimming? How would you do that with an orbital mission only?
It's a very interesting question and very fascinating to think that with an orbiter above the surface of the moon, like a few hundred of kilometers, we could deduce something about the interior, which is a few hundred of kilometers underneath the surface. We can do it. And in fact, the knowledge of this subsurface ocean, in particular for the Europa moon and the Ganymede moon, comes from the Galileo mission in the late 2000 from NASA. And they have detected those subsurface oceans thanks to a technique using a magnetometer. So if you have a magnetometer on board, you measure the magnetic field. It was mainly there to study the magnetic field of Jupiter. But when this mission made flybys of Europa and Ganymede, they find that the measurement of the magnetic field were a little bit weird and difficult to understand. And this is due to the subsurface ocean, which is a few hundreds of kilometers also for Ganymede underneath the surface. The liquid contains some impurities like salt. And then if this salty ocean is embedded into a magnetic field which rotates, like the one of Jupiter, it creates some electric currents. And as a result, you get some disturbance in the magnetic field around the moon. So if you have an orbiter with a precise magnetometer, even if you're a few hundreds of kilometers above the surface, you can detect some small variations of the magnetic field, which is due to the presence of liquid water, which behave in the big magnetosphere of Jupiter. So you see, in terms of physics, it's quite complex. But that's the way we can detect indirectly the presence of liquid water underneath the surface.
So this mission we're getting ready to launch in just a couple of weeks in mid-April. I know it's been a long time getting to this point, and as I understand it, this was originally going to launch last year. So
Correct.
I guess you had a delay somewhere. Can you tell us a little bit about that?
Yeah. So when we started the development of the mission, the schedule was such that we wanted to launch in June 2022, so last year. It was a very interesting trajectory. We wanted to arrive at the end of 2029. But mainly because of COVID, the COVID situation was quite a tough one for many people, obviously. And so we accumulated some delay. And at the end, we launched in April this year. So that means we have less than a year of delay, which, considering the challenges due to COVID, I think it's not that bad.
Not at all.
I have to say.
Yeah.
So this is how to explain the delay. So now we launch in April, and we don't arrive in end of 2029, but in July 2031. Every launch window has a different characteristics, and the duration of the cruise phase is different. The one we envisaged last year was a 7.5-year cruise. This one is more 8-year cruise, because the planets for which we do a planetary flyby, they are not always in the same position. The trajectory is very interesting. So we have different parts. We launch in April. We cannot go directly to Jupiter because JUICE is a very heavy spacecraft, 6 tons. Since JUICE is very heavy, we need to, instead of going directly to Jupiter, we need to make planetary flybys, gravity assist, to gain more energy at each time we fly by a planet. And then at some point, we have the necessary velocity to reach Jupiter. There will be 4 planetary flybys. First one in August 2024, so a little bit more than a year after the launch. And it's an Earth flyby. So we come back to the Earth to gain velocity. And that, this depending on the launch date, for example, if we launch really on the 13th of April, this flyby will be quite interesting. It will not be only an Earth flyby, because the moon will be around on the trajectory. So it will be a moon-Earth flyby. And that has never been done before. So that is cool. So I hope we launch on time. Then we can have what we call a lunar Earth flyby.
Well, that would be
and
exciting.
Then we continue. We make another orbit around the sun. We'll pass by Venus a year later, so in 2025. We go to Venus because Venus is also a big planet, so it's good for the gravity assist, so we gain a bit more of energy. Then we do another orbit around the sun. We do another Earth flyby another orbit around the Sun. We pass a little bit through the asteroid belt, and the last Earth flyby in 2029. And then we have enough velocity. We can go to Jupiter via the asteroid belt. So we have something like 4 orbits around the Sun, and it will take 8 years.
Right after you launch, I know that you don't get to just watch the rocket go up and then just relax and wait 8 years to get to Jupiter. You have a lot of work you got to do. So what are some of the steps involved in just getting the spacecraft ready to go once it's out of the launch fairing?
Yeah. So we have what we call the commissioning. You see that there are a lot of appendages on the spacecraft. So we have a big solar panels. We have a radar antenna, which is 16 meters long. We have a very long magnetometer boom of more than 10 meters long. We have a few antennas to deploy. We have also smaller booms for plasma physics experiment. And during the launch, they are all stored around the spacecraft because we cannot launch. So everything
is a really big spacecraft once it's
exactly
unfolded.
It's very big.
Yeah.
So everything is well packed, and when we are in space, we need to unpack. And that, if you see how the spacecraft look like, you see, wow, how are you going to do that? The first thing that we are going to do, of course, is to deploy the solar panels because we want to have power. That's the main thing, is to get power on the spacecraft. So after 1 hour, the solar panels will be deployed. And then for the next 15 days, we are going to deploy all the appendages. So we start with the small antenna, then the radar antenna, the big boom, etc. And every time we need to check that everything goes well. So that will be the first 15 days to deploy everything we need to deploy on the spacecraft. So that will take 2 weeks or so. And then we are going to check all the subsystem of the spacecraft. So the engine, all the star trackers, the camera, the software, the computers. And then we do the instrument, and we have 10 instruments, and some instrument includes many, many sensors. And that we have a long list of activities, and that will take the next 2 months.
So the magnetometer is clearly the most important instrument as far as detecting the saltwater oceans underneath the surfaces of these moons. But what other instruments are you flying on board JUICE?
We have 10 instruments on board JUICE, and they have been selected such that they can very complement each other, and they will allow to achieve the goals of JUICE. So you mentioned the magnetometer as very important. In fact, all the instruments are very important. We have really a great set of instruments, but we have also what we call a plasma package. It's a group of many sensors to measure all kind of particles around the spacecraft in the magnetosphere of Jupiter. So energetic particles, ion, electrons, neutrons, to understand the population of particles. And we have another instrument which is called the radio and plasma wave. So it's to measure also waves, plasma properties, electron densities, radio wave. Again, many sensors. So we all the in situ instruments, we are going to measure the environment of Jupiter. That's for one group. We have another group which are the remote sensing instrument. So we have a camera, of course, to study the geology of the moons, the atmosphere of Jupiter. We have a kind of camera which is called a spectrometer. So it will not take images, but it will record also the amount of light as a function of wavelengths, visible and infrared. And that means with this kind of instrument, we can get information on the composition of the surfaces of the moon. So what kind of ice do you have? What kind of molecules on the surface, organic molecules? And for Jupiter, the composition of the clouds and of the atmosphere. We have a UV spectrometer, so ultraviolet, and we have another instrument which never flew before to measure the properties of the atmosphere of the moon and of Jupiter in the particular range which we call submillimeter. It's to get information on the composition, the atmosphere, the atmospheric wind, and the temperature. So that's for the remote sensing. So a complete package to get as much information on the atmosphere and the surface of the moon, and very small atmosphere which is around the moons. We have a radar which will penetrate the ice of the icy moons over a distance of a few kilometers, so let's say 10 kilometers. So we'll see the structure of the first 10 kilometers underneath the surface. So it's quite interesting because nobody has seen that before. We have a laser altimeter, very interesting. So we'll shoot a laser pulse on the surface of the moon. We get the pulse back, and then we can measure the precise distance between the surface and the spacecraft. And from that, we can get the topography of the moon. And that is due to a particular process that we call the tide. So if I give you an example, if there is a liquid ocean inside Ganymede, the tides could be 10 meters high. So that means the surface will move up by 10 meters. And that we will be able to measure with the laser altimeter. So 10 meters, it's quite a lot. if there is no liquid ocean, that means all the interior of the moon is solid and the tide will be much smaller.
Right.
Because it's more difficult to make something solid moving than something liquid. And then the tide will be something like less than 1 meter, for example. And that's a way to detect the presence of liquid water.
So the amplitude of the tides, the
amplitude of the tide. Yeah.
Tides reveal the presence or lack thereof of subsurface water. Wow, fascinating.
And then we have an experience called radio science. So here we will use the telecommunication signal of the spacecraft to measure the precise trajectory of JUICE in the Jupiter system. And then from a precise measurement of the trajectory, we can have information on the gravity field of the moon and then on the interior structure. And for Ganymede, the idea is to get all the knowledge of what is inside the moon. So the different layers, the ice layers, the liquid layer, the iron core in the middle.
That's a very comprehensive package of instrumentation that you're bringing along. I mean, I can understand now why this spacecraft is so massive and why it takes so long to get to Jupiter. Just because you're trying to throw all of that mass out there. And
exactly. Since we don't go to Jupiter every year, once we go, we put the best possible instrumentation on board.
Well, there is going to be another mission arriving at Jupiter, probably around the same time as you will be. It's the Europa Clipper mission from NASA. Now, as the name implies, it's obviously going to be flying around Europa most of the time, but how do you suppose JUICE and Europa might work together?
So what is good is that the Europa Clipper mission, they focus on Europa, as the name entails, while JUICE will really focus on Ganymede and the other moons, so like Callisto, a little bit on Europa, and then Jupiter, the magnetosphere. So we are very complementary missions, so that's one good point. The second thing is that we have an excellent collaboration between the two teams. So we work together, we meet every year to discuss future plans, because I think it's fantastic to think that more or less at the same time, there will be two spacecraft in the Jupiter system. So that means we'll have two spacecraft from which the data can be analyzed together. And that's really, I think it's a fantastic chance for the scientific community. So in principle, Europa Clipper will arrive a few months before JUICE. So that means there will be maybe, given the mission lifetime, there will be maybe 2 or 3 years of overlap between the two missions. Given the trajectory, the two missions, we will have a lot of opportunities to work together. As an example, once doing the Europa flyby of JUICE, Clipper will fly by Europa only with 4 hours apart.
Oh, wow.
So there will be, the two spacecraft will be more or less at the same time around Europa. And to
that's
have
exciting.
Twice the amount of measurement, it's always much better. At the end of the mission, the spacecraft will impact Ganymede. That's what we call the disposal for Europa Clipper. And that's the natural end of JUICE, because we'll be in orbit around Ganymede. And once we are in orbit around Ganymede, there is no way to go somewhere else. So the two spacecraft in principle will impact Ganymede. So that means if we are lucky, if things goes very well, we could observe the impact of one spacecraft with the other one. With the other spacecraft.
Oh, wow. That would be cool.
As an example, Europa Clipper impacting Ganymede at high speed, while JUICE is in close orbit around Ganymede. That will be the best configuration. And we can learn a lot from studying an impact on the surface. So you can excavate the ice, material underneath the surface. It's also fun for the outreach, of course. It's fun to see an impact on the surface.
I didn't know that Europa Clipper was actually going to end its mission on Ganymede.
It's a possibility. It's not necessarily the final plan, but they have to dispose the spacecraft because due to planetary protection, they are not going to leave the spacecraft orbiting Jupiter. So they can impact Jupiter, they can impact Callisto or Ganymede. It looks like Ganymede is an option.
And I know that eventually JUICE will impact Ganymede as well, because as you said, you're going to be in orbit around Ganymede. And you won't have the delta V to get anywhere else.
Exactly,
But before that, I mean, after you've gone through your tour of the inner solar system and you finally have arrived at Jupiter, then you're going to be encountering Jupiter's radiation environment. And I'm just wondering, how do you plan to mitigate against that and keep your spacecraft alive for as long as possible?
First, we make sure we don't orbit too close from Jupiter. I would say that we stay at reasonable distances from Jupiter. We don't go closer from the Europa orbit, so that means we stay relatively safe. So that's one way to protect the spacecraft. The other way is that when we design the spacecraft with the industry, and the ESA project, we took the radiation environment into account, of course, and the spacecraft is designed to protect the electronics, the instrument from the radiation environment. So we have a special measure in terms of design. For example, we have some cavities inside the spacecraft with a lot of lead around to protect the sensitive electronics.
You have instruments shielded in lead wherever
Yep.
appropriate, and just don't get too close to Jupiter to begin with.
Yeah.
I know that Europa Clipper will be making a series of passes, like very high eccentricity orbit passes past Europa, just to spend as little time inside the radiation environment as possible. Are you considering a similar approach with JUICE, or will it remain overall closer?
For Europa, it's more difficult because Europa is relatively close to Jupiter. Then we have the radiation environment. So if we want to make a mission at Europa, one way is either to protect very well the spacecraft, so to have a very heavy spacecraft full of lead around, and you design a trajectory, as you said, for flybys, for example, to have an elongated orbit such that you spend some time away from the radiation environment. So we do 2 flybys of Europa, we do 12 flybys of Ganymede, and we do more than 20 flybys of Callisto. Wow. And we observe Jupiter from time to time. So we have Jupiter Peri-Jovi. And at some point, we use even the Callisto flyby as a gravity assist to incline the orbit with respect to the equatorial plane of Jupiter, such that the orbit will get inclined and we'll be able to observe Jupiter from higher latitude, so to see better the poles for study the aurorae and the magnetosphere. And then we come back to the equatorial plane, and then we end up in the Ganymede orbit. So JUICE has a completely different orbit compared to Juno and compared to Europa Clipper.
There's a long trip ahead of you, but it's also been a long trip just getting to the launch pad. What's going through your mind and your team's mind right now? How is the mood? Is everybody nervous, excited, pretty normal? How would you characterize everybody?
Pretty normal. I don't know.
There's nothing normal about this.
Pressure is building. That's clear. But now we are in the phase that it looks like everything is fine, and then we launch on the 13th of April, because now the spacecraft moved to another facility in Kourou that we will start the fueling. We just put the stickers on the fairing, the decoration of the fairing with the ring of a kid. So now things are becoming extremely serious, and I think now we say, okay, now it's okay. We are in the final straight line.
So when the launch fairing is decorated, you know it's serious. This is okay. Yeah, exactly. The stickers are on. We have to launch because the stickers aren't going to stay there forever. And I know that my level of excitement is nothing compared to yours and your teams. We've all done such hard work for so long, and this is still in many ways only the beginning, isn't it?
Exactly. That's another stage. It's the beginning of something else. That's the end of a phase. So it's quite interesting to change phase, I have to say.
That's exciting. And we have a long trip ahead of you, but it sounds like everything's going well. And I just wish you and your team all of the very best of luck with JUICE.
Yep. Thank you very much.
Thank you so much. Appreciate it. Well, I don't know about you, but I'm excited for JUICE. Can't wait for launch on April 13th, and can't wait for the next 13 years of mission. Wow, we got a long way to go. But thank you so much for joining us today, and thanks to these wonderful people for supporting me on Patreon. I couldn't do this without you. And if you'd like to join me on this journey through this incredible universe of ours, well, please make sure you subscribe and ring that notification bell so that you don't miss out on any new videos. Until next time, stay curious, my friend.